Okay, folks, good afternoon. The sign-up sheet is circulating around. Just a reminder, we have a quiz next week on Tuesday, and the topic that is going to be covered is switch realization. So starting from the semiconductor devices that we looked at, like the diodes and the MOSFETs and the IGBTs, and then looking into one particular single-pole, single-throw switch, first quadrant, second quadrant, on other quadrants, or single-pole, double-throw switches. You know, we are going to look into those in the quiz. As an example, let's take a look at the switch realization of this converter that we have analyzed before. This is converter that appears in cell H2 of that paper that we studied. So now, having the knowledge that we have, we want to see, for instance, if S1, is it a switch? Is it a diode? Is it an IGBT? What kind of realization does it have? So first thing that you may want to ask yourself is, why is it that we want to realize switches? Well, obviously, if you want to build this converter, you need to realize the switches. And other than that, you don't really need to realize the switches. You just assume they're ideal switches. And actually, we looked at some simulations that I already have uploaded on Blackboard. And here, as you can see, you don't really see any of the switches. It's just the equations, the mathematical equations that are actually applying to the converter. So if you just want to simulate the system, you don't really need to have any switch realization because it may make you actually a little confused. However, you may say, I don't want to simulate the system this way. I want to use Plex, and I want to use the diodes and transistors in Plex. So basically, you need to realize the switches. But anyway, for the sake of practicing, let's take a look at the switch realization here. First thing that we got to do is to identify the pairs of switches that we have. So here we have a single pole double throw switch over here, and we have another one over here. Well, this is assuming that they are not nicely numbered as 1 and 2 and 3 and 4. Obviously, in this paper, 1 and 2 are always together, 3 and 4 are always together. But let's say that doesn't exist in the topology that you're working with. The other thing is, in switch realization, we were looking at the throw voltage, and we were trying to find out if the throw voltage is positive or negative. And here it's easy because we have already analyzed the system. And if you remember, with this polarity, we got a positive voltage here, and the output voltage is actually appearing in this polarity. So we have already done an analysis for this converter. Like, if I remember correctly, VC1 was D times, actually I have it here, VC1 was D times Vn, which is positive, and Vout is also happens to be positive. So as long as throw voltages are concerned, for instance, from here to here, for instance, let me call it V throw number 1, and this is nothing but the input voltage. So throw voltage is positive, so no problem. And I'm going to talk about the other throw as well. But that's easy to figure out because we have pretty much all the voltages and capacitor voltages and everything. What about the currents? Because we also need to know if the particular throw pole current is positive or negative. In other words, we need to know the direction, the real direction of these currents. Is this current really positive in this direction? Is this current really positive in this direction? Well, we have done some simulations. If you remember, they turn out that they are actually positive. I think I just ran it already. So if you look at L1 and L2 currents, they are both positive. I mean, just focus on the very last few cycles. They are both positive in the direction that they are defined. Obviously, there is a little bit of ripple going on. I haven't run the simulation long enough. Long enough to eliminate that ripple. But assuming that the ripple is gone, both of the currents are positive in the direction. So one way would be you actually simulate the system in MATLAB and then kind of figure out if this is the correct direction for your current. But remember, your original objective was not to run this in MATLAB, so that's going to actually add some time, extra time. But what you can do is you can kind of look at the system and take a guess what is going on. For instance, I can argue that assuming that this polarity is positive, when I close this switch, this inductor will be charging this capacitor. So this current direction is probably positive. And when this switch is closed, and this other switch is closed, when this switch is open and this other switch is closed, we're actually doing something like that. So you can kind of take a guess what's going on. Or for instance, when switch S3 is closed, this inductor is now discharging this capacitor, which was previously being charged. And when it is open and S4 is closed, the current is flowing in this direction, which is the way it is supposed to be. It is supposed to be delivering some power to the load. And by the way, this may not necessarily, hold on. This very past thing, okay, this may not necessarily be the way the current is going to flow. The current is probably going to flow actually in this direction. All right. So you can kind of take a guess, but again, there is no way that you can tell for sure you are right or wrong. And assuming that you don't even know the polarity of the currents, you can actually go with the assumption that the current is bipolar, okay? It could be positive, it could be negative. Your switch realization is going to be a little bit more complicated, but then you can run the system and see what your real currents are and then eliminate that part of the, for instance, you're assuming that this current could be both positive and negative. That means you have to go, for instance, look at like a right half plane or a left half plane switch realization. Then you build it in Plex and realize, for instance, this current is always positive. Then you can reduce down your right half plane switch realization to either the first quadrant or the fourth quadrant, something like that. So you can always be innovative. You don't have to know everything from the beginning. So let's do it. Let's try to realize the switches S1 and S2 and also S3 and S4. So let me go back to a normal size. Okay, so let's focus on S1 and S2, and I'm just going to draw them in a way that, if you remember, we always assume, let me just go back and show it to you. When we were discussing switch realization, we always assume that this picture should always be in your mind, basically. Okay? So the polarity of the throw is, in a way, the voltage throw is, I'm assuming this is the positive one, this is the negative one. So the top one is positive, the bottom one is negative. And also the direction of the pole current is, it is flowing from left to right. And again, the way this system is drawn is, the throws are on the left-hand side, and the pole is on the right-hand side. So you always need to have this image in mind. Otherwise, things are going to get confusing. So having this picture in mind, let's go ahead and look at those particular switches. All right, so what I'm going to do is I'm going to redraw S1 and S2 in a way that I'm more familiar with. S2 is on top. S1 is down here. That is not a deal breaker yet. I'm just going to draw the inductor in this form. And this is the way IL2 is labeled. And let's say we already know that IL2 is positive in this particular direction. That means the direction that I'm assuming for my pole current is negative. All right, so this is what's important to me. All right. Also, the throw voltage from here to here, as I discussed earlier, is basically nothing but the input voltage, and we already know that the input voltage is positive, so no problem. Right there, this voltage is positive. So technically, you're looking at a fourth quadrant switch realization for this particular guy. So if you wanna if I wanna refresh your memory, let's go back and so we're looking at more like a boost type switch realization here. It's the fourth quadrant. The throw voltage is positive. The pole current is negative. All right, and that's it. So this is a fourth quadrant switch realization. Therefore, your switch realization is this. All right, so this is the switch realization for S2. It's a diode, and this is the switch realization for S1. Now here you have to double check something, and that is, in the end, usually one of these end up to be a transistor, the other one ends up to be a diode. You want to make sure that the original assumption that, for instance, S1 was the control switch is not violated here. So originally in the paper, it was assumed that S1 is the transistor to which the gate signal is applied, and as it turns out, S1 is a transistor. Now, what if S1 turns out to be a diode? Then you have to inverse that signal and apply it to the other, complementary transistor, okay? So for instance, in this case, if S2 was a transistor and S1 was a diode, then whatever command that you were going to apply to S1, you have to invert it and apply it to S2, which was a transistor. But here, not a problem. It works out pretty nicely. All right, questions?
Could I just say that this, just relabel it to S2 and S4, and I don't need to complement like 1 minus D or something like that. I just say that it's S2 and S4.
You could say S2 and S4. Okay, you could say that, but the voltage transfer ratio that you found was based on the assumption that S1 and S2 are the active switches. So you can do that, but then you have to go back and redo your voltage, voltage gain kind of calculations. Yeah, you can do that, absolutely. Same question. Okay, so yeah, you can do that. You can assume that S2 and S4 are the commanding switches, but then you have to go back and redo your voltage gain calculations. All right, so this was all about realizing S1 and S2. Now let's look at S3 and S4. I'm just going to redraw them down here. So this is S4, this is S3, and this is IL1, which we discussed. We already know it's positive, and the voltages are here. For instance, this is the output voltage. And then we have two other capacitors involved. This is just part of the system. This is not the entire system. I'm just trying to find out the throw voltage. Is it positive? Is it negative? Is it sometimes positive, sometimes negative? Okay. All right, so if you basically narrow down your loop that is dictating the voltage of the throw, it's something like this. So you can actually argue that the throw voltage VC1 plus VC2 minus Vn. So from the previous analysis that we had, VC1 was Vin times D. VC2 is Vin times the gain, which is 1 minus D plus D squared over 1 minus D. Then finally minus Vn. And if you simplify this, this turns out to be Vn times d over 1 minus d. And no matter what the value of the duty cycle is, this is positive. So I kind of took care of my throw voltage, and I know that no matter what the conditions are, the throw voltage is always positive. As long as the throw current is concerned, let me redraw this and make it even simpler. So I just realized this voltage is positive. Then let me redraw this in a way that I'm defining a very standard cell of a single pole double throw switch with a pole current that is negative. I just switched or swapped the place of the inductor to be on the right hand side to look like the standard way that I know. So again, we end up with a throw voltage that is positive, a pole current that is negative. So again, we are looking at the fourth quadrant switch realization. So this is a diode, S4 is a diode, and S3 is a transistor. Okay, and that's it. So again, you got to check here. S3 ended up being a transistor, and originally the assumption was S3 is where we are applying our gate signal. So there is no contradiction here. Again, if S4 turned out to be the transistor, you had to reverse S3 to get S4 basically. All right, so this is all we got, and we got to go now and actually do some, let's say, Plex simulation. The only thing to remember is I have actually twisted the configuration a little bit, like S4 in the original configuration is a horizontal kind of a line, so this diode has to basically rotate for like 90 degrees or something like that. All right, so looking at the simulation, I've already done this in Plex. Oops, let me close anything. All right, similar to what we actually I had on the screen earlier, S1 is a transistor, S2 is a diode, S3 is another transistor, and S4 turns out to be a diode. As long as the gate signals are concerned, I am applying let's say 50% duty cycle. I'm trying to compare this results versus the MATLAB-based results. So I'm trying to replicate the same input voltage and the same duty cycles. Frequency 100 kilohertz. Duty cycle 0.5, frequency 100 kilohertz, duty cycle 0.5. And you run it, and you end up with a waveform like this for the currents. Well, actually, these are the voltages. So you get an output voltage that is close to 72 volts. Yeah, it is 72 volts, and if you go back to MATLAB simulation, it gives you the same thing. Let me see. Output voltage. Okay, here it is. So it is giving me 72 volts here, assuming the transient is over. So my point is, these simulations are giving you basically the same results. Plex, you need to have switch realization available. Once you have switch realization available, it's easier to do it. But then in MATLAB, you don't need to have to do any switch realization. It's ideal switches. It can do anything you want. But then it may take a little bit of a longer time to do it. Any questions? So your quiz might be something similar to this, or maybe a little bit simpler than this, that, hey, we have a converter, ideal switches are there, and I'm asking you guys to realize the switch for that particular converter. All right? Any questions?
Would MATLAB just have the equations, like integration equations developed, and Plex would have the components? Like in MATLAB, we just have to develop the integration equations?
You don't have to. That's what I prefer. MATLAB also has SimPower toolbox. Assuming that I can open it somewhere. They have it. How do you guys run simulation?
Go to the library.
Library. Where's the library?
Yes, that
Here?
The main page.
The four rectangles.
Yeah,
Next to
This one?
Yeah.
Okay. All right, well, thank you. I didn't know. Okay. What happened?
Yes.
Okay, there it is. So MATLAB also has SimPower somewhere. I don't remember where it is because I never use it. Simscape. Okay, Simscape. You guys, okay, here it is. And then SimPower systems. You can actually use, like, it has models for instance, diodes and MOSFETs and things like that, like power electronics. It has models for this. But in the past, I was never successful with doing this because you get a lot of convergence errors, basically. So my advice is, do not use a particular model unless you exactly know what is going on in that submask. And again, in Plex, you don't have to always do it this way. Plex has all the capabilities that MATLAB has. You can actually create this MATLAB model that I have also in Plex. So you don't have to do it, using, it's just more convenient. All right, so this was all about switch realization. We are going to move on to a new topic, which is the Fourier analysis of converters. So it's a relatively short topic, but very interesting. Could be very useful sometimes. Okay, so as you noticed, a lot of times when we are applying a gate signal or a command to a switch, that command is a periodic signal. And then the behavior of the system, like your inductor current has a periodic behavior, the ripple that appears in your output voltage has a periodic behavior. So you may argue that everything is pretty much in a power converter is a periodic signal with a period of your switching frequency. So, and the other thing that we can remember is if something is periodic, it could be described using the Fourier series component of the signal. So that's what we are going to do. So I'm going to start with the Fourier basically definition of a periodic signal. It would be, it doesn't matter mathematically, but for the sake of convenience, I'm assuming this is the command that I apply to a switch. Just call it H or existence function or something like that, or switch command. And as I said, this is a periodic signal, so it just periodically repeats itself. Okay. All right. So remember, this is dt. Okay, and this is one period. Now, why am I shifting things in a way that things are kind of symmetric? The reason is if I do so in my Fourier series, only cosine terms are going to appear. Otherwise, you have both cosine terms and sine terms, and it's going to be a little bit more complicated. All right. So going back, again, this is a periodic signal. Going back to the Fourier series, I can write it in this form. The command that is applied to the switch has a kind of a DC component plus bunch of AC components. So So n is the indicator of the harmonic. Like if n is 10, we are looking at the 10th harmonic of the signal, which is happening at cosine of 10 times omega t. And by the way, omega all of a sudden is 2 pi over t. T is the switching period, basically. All right. The way the duty cycle is defined, actually the DC value of, oh, by the way, this peak value is 1, and this bottom value is 0, obviously. Okay. So the way the signal is defined, the average value of the signal is D plus, we are not going to do it here, but if you do some Fourier series analysis, you're going to realize that H sub n, the amplitude of the nth harmonic, looks like this. Okay. So a lot of power electronics book, if you look at the end of the book, there's a table that is introducing a bunch of waveforms and then introducing like the amplitude of the fundamental, of the harmonics of that signal. So I'm assuming that I had one of those books and I have actually obtained this part from that book, for instance, or that table or something like that. All right. So let's say I have this knowledge and I, for instance, want to focus on one particular converter and see what kind of information I can obtain. Usually you go with the simplest converter possible, which is the Bach converter. So let me just focus on the Bach converter. Okay. Okay, I'm just going to call this voltage Vx, and you're going to see why. So this command, I'll just call it h of t. And by definition, if this signal is 1, that means the top throw is engaged. If h is 0, that means the bottom throw is engaged. Okay. So technically you can, okay, in a very general case, if I call this voltage V1 and I call this voltage V2 with respect to any point, I can argue that Vx is V1 times plus V2 times 1 minus h. 1 minus h is the complement of h, which is this command. Hypothetically, it's the command that is applied to the bottom throw, basically. In this case, V2 is 0, so Vx is nothing but V1, or Vn, basically, something like this. So all of a sudden, you can see that if I can describe my command to the switch in a Fourier series form, I can also describe Vx is in a Fourier series form. So technically, Vx is Vn times d plus cosine of omega t plus, for instance, 2Vn sine of 2 pi times d over 2 times pi times cosine of 2 omega t. And so on and so forth. All right. So this could be a description for Vx. I just multiplied what I had for h by Vn, and I kind of expanded my series a little bit. All right. So if you look at the Vx to the right, if you look at the right-hand side of the circuit, you realize that the system is a linear time invariant kind of a system. We have one L, which is a constant value. We have one capacitor, and assuming that your load is constant, everything is constant. Nothing changes by time. There is no switching configuration going on. It's not a variable structure. So if you have a linear system, you can actually always remember to take advantage of superposition. So now that I'm actually Vx, which is the voltage that is actually appearing like as an input to this right-hand side of the converter, and Vx is described in terms of a bunch of terms, I can argue that at any given time I can include or consider one of these terms, find my response, and then in the end add all of the responses together, kind of what you do for a basically linear superposition. So technically I can argue that in order to find the answer, for instance, my answer that I'm looking for is V out or IL or something like that. In order to find that answer, what I can do is I can break down my system into its components. So this would be equivalent to one time, considering this term. Let me just draw like a little bit of a red here and a little bit of a red here. One time I can consider the DC component, which is V in times D. I'll rewrite it. And then look at the rest of the network and actually calculate that response. All right. So this is going to give me some current waveform, which is going to be the DC component of the inductor current. All right. Then add that response to a system that is excited by a sinusoidal system, sinusoidal source. And that thing is basically this term. Just going to draw blue here. So this sinusoidal signal is nothing but 2Vn times sine of pi d over pi times cosine of omega t. And then this is going to give me this current waveform, which represents the harmonic, the fundamental or the first harmonic of the inductor current waveform. And then I just have to keep doing this. So now this time I'm going to use another color. I don't know. Let's do green. And depending on how accurate my response is gonna get, I have to actually, I need it to be, I have to keep actually adding other components to it. So this one would give me the second harmonic in the current waveform, which is the ripple. Then once I have the current information, I can find, for instance, the output voltage information and things like that as well. All right. So if you look at this, kind of expansion or like a superposition expansion of what we have, you can see a lot of times you're applying this an AC signal to the system. Like if you're looking at the first harmonic, then the second harmonic, and the third harmonic, and so on and so forth, they are all AC sources. And with AC sources, we can always define an impedance. So I'm just going to define an impedance, which is dependent on what harmonic I'm trying to study, and is still counting the order of the harmonic. So this is basically nothing but this impedance, described in a very general form of N, basically. All right, so now I can write IL a DC component. Again, a DC component is not a function of time, but let's just put it there anyway. Okay. And then once I have the current, I can, for instance, find the output voltage and so on and so forth. So for instance, once you have this current, you just have to multiply that current by this impedance over there to get the output voltage, and just keep doing that. All right, it sounds a little bit cumbersome, but you can get really good at it, and it sometimes gives you a lot of valuable information about the signals in your system and what harmonics are important. If you are trying to, for instance, look at the lifetime of a particular capacitor and see if the particular harmonic is, for instance, degrading the performance of your capacitor or something like that. Now, I do have a kind of a MathCAD emulation of what is going on. So actually, let's take a look at that. And I'm going to put this on Blackboard as well. Again, if you are not familiar with MathCAD, familiarize yourself with MathCAD, because a lot of times we are using MathCAD to basically do a simple, math rather than MATLAB. All right. So in MathCAD, you have to define everything. For instance, we are defining J, which is the imaginary number, which is the square root of -1. Here, the input voltage of my buck converter is 48 volts. The inductor is 100 micro. The capacitor is 10. Load resistance is 6. The reason that I'm defining these values is I'm going to define the impedance. And in order to know the impedance, you need L and R and C and things like that. All right. So my frequency is 100 kilohertz. Omega is 2 pi f, or 2 pi over T. And the duty cycle is 25%. So I'm expecting my output voltage to be 12 because the input voltage is 48 and it's a buck converter. Now, this is nothing significant. I'm just trying to get a good resolution waveform. So I'm actually kind of defining the kind of an array of times. So when I'm drawing a signal or plotting a signal, it is calculating it at all of these basically particular points. This has nothing to do with the math that we are trying to work with. N is counting the harmonics. 0 means we are looking at a DC signal. Then 1 means the first harmonic and the second harmonic. And potentially I want to go up as high as 100, harmonic number 100. So Z that we just defined, which is that impedance of, the L placed in series with a parallel R and C. And I'm looking at 1 over Z over here. 1 over Z, 1 over the magnitude of Zn. This is important for me because this kind of determines, so basically if I go back here, generally speaking, remember Vx is Z times IL, something like that. I'm assuming things are AC. It's not a true statement, but anyway. So Vx times 1 minus Z is kind of IL. Now I'm looking at 1 over Z in this graph over here. Kind of telling me that if the order of the harmonic increases, 1 over C in terms of magnitude gets really, really small, and that explains that if I have a bunch of harmonics in my Vx, let's say harmonic number 10, 1 over Zn is very, very small. Therefore, that 10th harmonic is going to be attenuated when I'm looking at the 10th harmonic of my current, basically, something like that. And that's a good thing because you're ultimately trying to eliminate all of the harmonics and only get a DC output voltage. So it makes sense for 1 over Zn to be significantly large or having a significantly large DC value or n equals to 0. And then as the order of the harmonic grows, your 1 over Zn should actually attenuate. Now I'm actually defining my switching function. Nothing, it's just a symmetric waveform. I'm just focusing only on one period, negative t over 2 to t over 2. And the duty cycle, as was defined earlier, is 25%. Now, these are the amplitudes that appear in my my Fourier series. So if n is equal to 0, the amplitude is d. Otherwise, it's this 2 times sine of n times pi times d over n pi. And this exactly comes from basically this expression over here. All right? All right. So I'm also drawing or plotting, I don't know, since we can, in MathCAD, it's really easy to plot things. We are also plotting h of the existence function. As you can see, it has a DC component, which is 25%, which is our duty cycle. Then unfortunately, the first harmonic is even larger than the duty cycle. And remember, we only care about the DC value in the end because we want to have a DC output voltage. All right. So here I'm actually writing down my Fourier series, which is those amplitudes of h sub 1 times cosine of n omega t, and I'm actually adding them up together. So if I add them up all together, I'm just trying to double check things and make sure if I make sure that the Fourier series expansion that was provided to me is accurate. In other words, if I add all of these terms, I should end up with that square-shaped existence function, which is basically this graph over here. All right? So I'm adding the first 10 components, and I get something similar to that. But if you are not happy with that, you can actually increase the order to, let's say, 100, and it gets very close to what you expect to see. As it turns out, you don't really have to go to extreme numbers. Even 10 is more than what you need. So this was just double checking that your Fourier components are accurate. All right. So I'm trying to find or reconstruct, using the Fourier series, the inductor current. Remember, the inductor current is the input voltage times H1. So this Vn times H is giving me basically my Vx. And then Vx divided by Zn is IL. This is basically nothing but this equation over here. All right? So I'm trying to look at the current. So as you can see, my inductor current looks good in a sense that it doesn't have a lot of high harmonic contents. It has a relatively significant DC component, and then it has some actually components in the first and second and maybe third terms. And if you want to double check, the DC value of the inductor current is 2 amperes. This is because input voltage is 48, duty cycle is 25%, so the output voltage is supposed to be 12. Load resistance is 6. 12 divided by 6 is 2 amperes, and that is actually the average value of the inductor current as well in the buck converter. So I'm not surprised to see this 2 over here. All right. So now that we have all of the harmonic content of the inductor current, you can actually maybe add them up all together and see what it looks like. So if you add them up all together, you got to be careful when you're adding them all together. You also have an argument of IL, so you have to consider that as well. So it gives you a waveform like this, which is a triangular, basically, waveform, which we expect to see for the inductor current. And as you can see, even I'm only considering the first 10 harmonics, and the inductor current is relatively triangular as I expected. But like if you do go from 10 to 100, it doesn't really make a significant change. So you can see that 10 was a good number. Now, let's say you're lazy and you don't want to do even 10, you may want to consider doing only 3 of them. You see, it's still relatively good. What about 2 of them? Gives you like a little bit of a distorted AC signal. What about none of them, or just the DC component? It only gives you the DC component of the inductor current. So I would say even number 6 would be good. Yes, it's a relatively good prediction of what is happening to my inductor current. So this could be useful, for instance. For instance, you are using a particular core, and you have a very good model for the magnetic material of that core for each individual harmonic. Now you have the content, all the harmonic content of your current. You can, for instance, have a good or accurate calculation about the losses in your, for instance, magnetic core. All right. Now once we have the inductor current content, we can, for instance, look at the output voltage. Now in order to do the output voltage, look at here. So all I got to do is I can say V out is IL times this Z, let's call it ZX, and ZX is nothing but a resistor in parallel with a capacitor. All right, something like this. So this is what I'm doing over here. So I'm again saying the output voltage is the inductor current times basically a resistor that is placed in parallel with the capacitor. Now looking at the harmonic content of the output voltage, as you can see, we have a 12 volt DC component, which is this 12 over here, and then pretty much we have nothing else. That's good. That's what we want. We wanted to have a DC output with almost no ripple. So once that I have all these harmonic content, I can also add them up all together in terms of a time form and see what my output voltage looks like. And this is your basically output voltage. You can see it's almost a DC signal. It has a little bit of a ripple. If you zoom in, let me just, for instance, do it from 11 to 12 or maybe 13. All right, so you can actually identify, maybe zoom in a little bit more, like 11.8 to 12.2. So you can see the similar pattern that you have seen in a MATLAB simulation, for instance. You can see that this also appears in your output voltage, which is the pattern. And as it turns out, because we have assuming that we have done a good job in designing our filter, even if I look at the first 2 harmonics, it doesn't really change much. So that means that all of the higher order harmonics are basically all disappeared. The first and the second harmonics are good enough. If I just keep the first harmonic, it just gives me an AC signal, which is almost a good approximation. Sometimes you can, for instance, approximate the ripple of your output voltage just considering just the only n equal to 1, the first harmonic that appears in your output voltage. So this is one way of analyzing a buck converter. It's not time basically based, it's frequency based. And a lot of times it gives you good insight about what is going on in terms of the harmonic content of your system. For instance, you're doing some noise analysis. You want to see a particular, for instance, frequency, how much it appears, and then, for instance, you're looking at the layout of your system and things like that. Now, I'm going to post this thing up on Blackboard, and then you can play with it. For instance, you can change your duty cycle from 25% to 75% and see, for instance, what happens in the inductor current waveform. Well, what happened here? Anybody has an explanation? Why did it disappear?
Went off the scale.
Right, so I increased the duty cycle. Now my output voltage is 36. Divided by 6 ohms, it is 6 amperes. So I have to change the scale to maybe 9. And it's back, basically. Okay? Same story for the output voltage. So don't be surprised if things disappear. That's because your scale is, let me do the 0 to 30. 0 to 40 maybe. Or it's just a flat DC. Obviously, our scale is too large. We can't even zoom into the ripple of the output voltage. All right, so I put it there. This might be a good exercise for you. If you're not familiar with MathCAD, you may want to actually start playing with this and become just a little bit familiar with MathCAD. It's a very, very actually interesting and easy tool to use. Any questions? All right. So this was a very simple version of a Fourier analysis. That's pretty much as this course is concerned. Now, in a lot of places, when we have an inverter or when we have a major AC component in our signal, again, we become actually interested in Fourier analysis, like in a rectifier or in a power factor corrector or things like that. And then there are modeling approaches, which is called like generalized state space averaging, things like that. So you actually look at the harmonic content of your signal. So if you're interested, let me know. I can actually provide some literature for you guys. All right, no questions. Now we want to move on to a very important topic, which is going to take a lot of our time, a lot of the basically portion of this class, which is called power converter modeling. All right. So my assumption is everybody here has had some sort of a course related to controls. If not, no problem. But anyway, when you take a control class, you are dealing with a system that has an input, has an output, has a feedback loop, and you are trying to either regulate something or track something or something like that. So. And then we have transfer functions, and those systems are usually linear time invariant systems, and power converters are not. So why, if you ask about why is it that we need a model for our converter, the answer is because we want to control our converter. Because a lot of times you're looking at an application that your, for instance, desired characteristic is to have the output voltage absolutely constant no matter what the value of the load is. For instance, for the motherboard of a computer, you're providing power to the central processing unit of the computer, whatever it is consuming, I don't know, for instance, let's say 50 watts. And depending on what you're doing with your computer, then the number varies. For instance, you are running a very heavy simulation, for instance, you're using a lot of power, and then later on you pause it, and then you don't consume a lot of power anymore. So the load, which is like that resistance that is connected to your buck converter, is highly unpredictable and variable. But then the voltage that the CPU is being fed with is supposed to be absolutely constant. If all of a sudden it drops to 0, then the CPU turns off, or it goes to overshoots to a certain value, you may actually damage your CPU. So there's a high dynamic in your load, but your converter, regardless of that high dynamic, should be able to provide a constant voltage to your CPU. I don't know, 5 volts or 4 volts or 3 volts or 1 volt or whatever these days they are using. On the other side, you may argue that there are applications that your input voltage is variable. For instance, you're trying to I don't know, charge your cell phone while you're driving. Your cell phone has a battery, the voltage is almost constant, let's say 3.7 volts, but the input voltage, which is the voltage of the battery of the car, the nominal number is 12 volts, but depending on the state of charge, it may be 14 volts, it could be 9 volts. Or it depending on what is happening in the car. For instance, if you're starting the car, there might be a huge current being drawn from that, and then that even 12 may drop into maybe 6 volts temporarily. So your input voltage is a variable voltage. Your load would like to see again a constant voltage of 3.7 volts. So sometimes your input source is variable, sometimes your load is variable, and then you should be able to regulate the output voltage regardless of the changes. So that's why we are trying to look at a converter from a controlled perspective. Why is it that we need a model? Now, the terminology that you are going to hear a lot in power electronics is called small signal model. Now, why do we call it small signal model? The reason is, if you look at, for instance, our the Fourier analysis that we just did. Let me just bring it up here real quick. Let me go back to 2.5 duty, 0.25 duty cycle, so things are in a scale. For instance, if you look at the harmonic content of your inductor current, you can see we are looking at a signal which is triangular, but if you look at the harmonic content, we have a relatively large DC component and bunch of ripple. If you look at the output voltage, you can see actually the same thing. You have a relatively, or in this case, significantly large DC content versus or compared against the ripple. So to make things simplified in power electronics, a lot of times you assume that your signals, for instance, your output voltage, for instance, your inductor current, and sometimes even the signal that is applied to your switch. You assume that these signals have a large DC component, and then in addition to that large DC component, there is a little bit of a fluctuation riding on that DC component, something like that. So you're assuming that your converter is operating under steady state conditions, everything is relatively constant, and then in addition to that, you are, your load is, changing a little bit, or your inductor current for a weird reason is changing, or your input voltage is changing, or something like that. So you have a large signal, and then you have a small signal variation riding over that large signal. This would be as if you, for instance, are trying to, so this is to justify a small signal model. Let me just write it here. If you consider like a microelectronics example, a good example would be, for instance, a diode. All right. So remember when you were taking electronics 1 or 2, you were doing a DC analysis, then an AC analysis, something like that. So the DC analysis, so this is, for instance, a diode we are talking about. A DC analysis gives you the operating point. Then in addition to this DC analysis, for instance, you're looking at an amplifier, you have some variations in your, for instance, current. All right, assuming that this is sinusoidal and my drawing isn't good anyway, so, and then that causes some variations in the output voltage. All right. So we have a large signal, which is a DC signal. In addition to that, there are some perturbations. So since the 70s, when they started modeling converters, because they had this microelectronics mentality in their mind that, okay, everything is DC first, let's analyze the system, and then let's perturb the signal and see the system and see what happens. So like in a diode, for instance, for a small signal model, you could say the voltage of the diode is some resistance times the current of the diode, or something like that. And that resistance is kind of signifying, let me see how much I can zoom this. That resistance is actually highlighting this slope basically. Something like that. So you have seen things like that when you're trying to model a transistor or something like that. So equivalent to that in power electronics would be something like this. All right. So let me draw it. So let's say you have a power electronic converter, for instance, the Bach topology. All right. I label this signal to be Vx and IL. So we just did some Fourier analysis and we realized that, for instance, Vx could be described like this. A DC component, which is Vn times D. D is the duty cycle, and bunch of higher order harmonics. And that causes IL to be like some DC component plus a bunch of harmonics. So what we do is we assume temporarily that these guys do not exist. We only look at signals in a DC way. We only look at the DC content of all of the signals. And then we assume that in addition to this DC content, there is some ripple or there is some small signal riding on that. So let me just try it over here. So if I just look at the DC model for my converter, I end up with this. All right. So the DC model for my converter is basically a DC transformer, basically, right? So Vx on the output kind of the transformer is Vin times D, and IL will be reflected to the primary side. You can actually write the content of IL or something like that. All right? So first is a DC analysis. All right. Then we add perturbations. And also linearization. I'm going to talk about it. Okay. So perturbation is assuming that, for instance, my input voltage is a DC signal plus some small signal variations. I use this little hat on top of the name of the signal indicating that this is a small signal thing. And in order to emphasize that it is really a small signal, I write it this way, meaning that the in terms of magnitude, the time-dependent portion of the signal is way much smaller than the DC or the time-independent portion of the signal. And I kind of do it for pretty much all of the signals in the system. For instance, I would say IL has a DC component plus a small signal variations. Okay, and even again, I define duty cycle as a signal too. Again, duty cycle is just a number; it's not a signal. But a lot of times, in a lot of textbooks, you see duty cycle as a signal. This is actually that S or H, the command that is applied to the switch, in which duty cycle is determined, basically. So again, I have a DC component for the duty cycle plus a small signal perturbations. All right, and for instance, I don't know. I'm keeping going with this Vx thing. I have to change my notes a little bit, or maybe not. Let me just write it here. Let me just write Vx. And pretty much everything, like for instance, I1, the primary side current or something like, or the source current. Okay, so something like this. All right, now I'm going to do some math here to basically, for instance, look at this equation. So in a DC way, I can say the DC value of Vx is the DC value of the duty cycle times the DC value of the input voltage, right? Now, I kind of generalize the signal and write it this way. Vn times D and then I replace Vx with its DC component plus its ripple. For the input voltage, on the very first line, I have a DC component for the input voltage plus some ripple, a small signal ripple, multiplied by, for the duty cycle, the same story. We have a large DC component for the duty cycle plus some small ripple, something like this. So if I expand this multiplication, All right, this is what we're getting. So you get 4 terms on the right-hand side. And obviously this side we have Vx plus ripple of the Vx. All right? So if you look at this portion is telling me that the DC value of Vx is the DC value of the duty cycle times the DC value of Vn. This is what we had earlier already from our very small DC model. So this part is not a surprise. The other thing that we are going to do is we are going to say this term is negligible. Why is that? Because we have 2 small signals multiplied by each other. So they are both very small, less than 1. When you multiply them by each other, it's even get further smaller. So even smaller. So then you can actually eliminate that. So this is actually kind of, you're linearizing the system by when both perturbations, they are both small signal perturbations, are multiplied by each other, you assume they are basically 0. Okay? Now, I'm going to do almost the same thing for the primary side current. Do we have time? Yes, we do. All right. So looking at this model, I can argue that since I have this transformer, like a DC transformer here, I can say in a DC way, I1 is IL divided by D. Is that correct? No, IL times D. All right. So I'm going to generalize this down here and say I1 all right. So now again, I'm replacing I1 with its DC component plus a small signal ripple, IL times, same thing for the duty cycle. And then you expand it again, you end up with IL times D plus D times the small signal perturbations in the inductor current plus a small signal perturbations in the duty cycle times IL plus both small signals multiplied by each other. And similar way, I just assume that this last segment is almost 0 or negligible because I'm linearizing the system basically. All right, and if you look at the DC terms over here, you have the DC value of I1 is the DC value of IL times D, which is what we already had here anyway. So that part is not a surprise. All right. So having these 2 equations, I'm going to expand this very simple model that we had as a basically DC equivalent circuit to something that is a bit more complicated. Let me just draw it over here. So for instance, I'm trying to construct I1. Or basically perturbations in I1. Maybe I should do it next time. What I'm trying to do is I'm trying to look at this term and say, okay, this term is this term plus this term, and then try to find an equivalent circuit model for it. So I think I don't have, it's a little bit big, so I don't have time to do it now. I'll see you guys on Tuesday, and don't forget about the quiz. We have a question.
Actually, I just wanted to confirm that the harmonics that we're talking about are not a part of the perturbation, like they are just part of the steady state system, but
The harmonics. Well, that's how you can debate. You can argue that these harmonics that we neglected here, they represent the ripple. I mean, it depends on the system. Sometimes you have a major AC component that you cannot neglect, for instance, in a PFC application. But here you kind of say these harmonics are representing the ripple, or they're representing the small signal variation in the system. Or you can argue that no, they are not. A small signal variation comes in when my input voltage is changing gradually, something like that.
because what the small signal was like, I mean, because I thought that small signal represents is that whenever you have a perturbation in an input voltage or a load resistance or
Right.
something external to the circuit changes, that's what causes you to...
Yes, but those changes may actually cause some harmonic changes as well. So we are eliminating the harmonics and say, yes, our input voltage may change in a slow, low frequency, a small signal variations. And they may cause some other harmonic somewhere else. All right, we're going to see it next time. It's a little bit confusing now. All right, see you guys next week on Tuesday. All right?